All right, so welcome back. This is now, I don't even know what lecture we are because I've lost track from however long ago it was. But we have at this point covered the material from the first two exams. The first two exams would be everything up to the basics of confidence intervals and hypothesis testing. Yes. Right. Thank you for reminding me. Thank you for reminding me. I have forgotten. Because my other high school, we no longer have to wear it, so I have forgotten. Thank you. So up until now, we have done one situation of confidence intervals, and we have done one situation of hypothesis testing. The next few chapters, essentially really till the end of the course, are all of the other examples of confidence intervals and all the other examples of hypothesis testing. Luckily, from a computational standpoint, you're essentially doing exactly the same thing for all of them, because every problem is a calculator problem. And if you actually take out your calculator and you look, for example, at either the testing portion or the confidence interval portion under the stats and tests, what you'll see, how many tests do we see there? How many intervals do we see there? There should be 6 of each, right? There's 6 of each. Hello, hello. Right, we all agree, 6 of each? So the next few chapters, up until the last 2 chapters of the course, are going to be the other tests and confidence intervals and when do we use them. But at the end of the day, when it comes to actual computation, you just plug things into the calculator and the calculator pops out the answer. So we're starting with chapter 18. And chapter 18 is on comparing 2 proportions. So we've already done 1 proportion, both for confidence intervals and hypothesis testing. It feels like, well, we'll see how good it is. We've done confidence intervals and hypothesis testing for 1 proportion. So let's first recall that. Let's first recall for 1 proportion. What was the formula for the confidence interval for 1 proportion? For proportion? For proportion? What? X over n. X over n. Sarah, what's up? Good. X over n, which we call p hat. That's our sample value, p hat. Plus or minus z star square root p hat 1 minus p hat over n. This was a formula for 1 proportion, and essentially you really only need 3 things to put into your calculator. The 2 things that comprise p hat are x and n, and that covers this p hat, that covers this p hat, and that covers that n. And the 1 thing was the z star. Basically, you have to give it your confidence. So you give it those 3 things, and I'll pop the confidence interval. Successes, number of trials, confidence. We also did a hypothesis test for 1 proportion. We had a null hypothesis that the true value of p was equal to some value p naught, p sub 0. And then we had 3 possible alternatives, p being greater, p being less than, or p being straight up not equal. And how did we go about computing the p-value, determining whether or not we were to reject or not reject the null hypothesis? We again went directly to our calculator. And on the calculator, how many things do we actually have to input to do a hypothesis test for one proportion? We didn't put in P. Oh, P, yeah, you had to put in P naught, your assumed value, the number of successes, and the number of trials, because that gives you your P hat. So those three things are, again, all you needed to work with hypothesis testing and come to a conclusion based upon your p-value. Once you get your p-value, you would compare it to alpha, so you had to be provided one more piece of information. But nevertheless, this is how we did one proportion. This is all stuff from the last test. Hopefully it's somewhat familiar, if not very familiar. Now, we're going to work with two proportions. And essentially, a two proportion example is when we are comparing two proportions. So we're not saying, hey, I believe the value of the proportion is 0.5 or 0.8 or 0.3 or whatever, but we're saying rather, I wonder if that proportion is the same as that proportion. Do men do it better? Do women do it better? Are their proportions equal? And so on. Right-handed versus left-handed, are they equal? We're comparing two different proportions now. And because of that, these formulas don't make any sense anymore. These formulas only have one proportion in them. How could they make sense? Correct? So all we need to do really is update the formulas to this new scenario and then plug everything into the calculator and get our answer. So let's see what these new formulas are. I'm going to keep those up there. And I'm going to go now for two proportions. So let's consider what our data is going to be if we're dealing with two proportions. If I want to know whether right-handed or left-handed people are better, or whether dogs or cats are better or higher or lower, whatever the case may be, I'm inherently going to need to take two different samples. I'm going to need one sample for the first group, and I'm going to need a second sample for the second group, correct? Yes.
Does the sample size matter?
The sample sizes matter in the sense that both numbers are going to play a role. They don't have to be the same. But I will have to take two different samples, correct? So the first things I'm going to need are N1. What do you think N1 is referring to? The first sample size. I'm going to need N2. What is N2 referring to? The second sample size. I'm going to need X1, the first sample number of successes. I'm going to need X2, the number of successes in the second sample. What else did I need here for confidence intervals? I needed Z star, which ultimately comes from my confidence. So I'm still going to need my confidence level. I'm just going to use Z star here because Z star comes from the confidence. They're one and the same. How are you? Good to see you. And that should be all we need. So let's take out our calculator and let's go to the confidence interval for two proportions. Yeah. Because mathematically, if you go through the derivations for where these formulas that we're going to come from, they just don't have to be the same. I can't go into the I can't get too technical here. Okay, but mathematically, because think about it. You take two samples, the sample sizes are not the same. Oh, well, can't use the data. I mean, you have data, right? Use it as best you can. So these formulas were developed for any scenario. Okay. So if you go to your calc, yes? No, this is the confidence for this problem.
Oh.
Okay, I want a 95% confidence interval for the difference of my proportions. Because at the end of the day, by the way, that's what we're doing here right now. In the first case, this was a confidence interval for what? What were we after in the first example? Huh? I can't hear you. No, I know, but what were we trying to figure out in this one proportion test that we did? This confidence interval. What are we trying to determine?
Within a certain model of confidence, the range of possibilities.
For what though?
Your outcome is correct.
For what?
That your outcome is correct.
But what were we trying to, physically, what are we after? We're after something, one thing. Which one? Now, the p-value tells us whether to reject or not reject in the, huh? The p of the population. This is a confidence interval that is trying to hone in on the true value for the population. P hat is my sample proportion. P naught is my assumed proportion. But what is the real proportion? I don't know. But this is a confidence interval that hopes to catch it. The smaller my confidence interval, the more reliance, the more trust I have that I found it, correct? So what am I after now for two proportions? What's my confidence interval for? My confidence interval, which at the end of the day is an interval, what am I trying to catch there? Huh? No, it's a specific, here I was after the proportion. A very specific thing, the population proportion. That's what I'm trying to catch. What am I trying to catch here? Well, better, worse, I don't know what better means. Sometimes the smaller value is better. It's a quantity. It's a mathematical quantity. Here, what I'm trying to catch is P1 minus P2, the difference in their values. The first true value proportion minus the second. I am after P1 minus P2. This is the quantity that I'm looking for. I don't know if it's better or worse because I don't really know what it is that I'm after here, but I am after the difference in their proportions. If P1 minus, yes?
Can you give us an example of this? Like,
Of course. So you're asking if I would do what any good teacher would do? Yeah, sure,
so
okay.
like, let's say you're using the left hand, right hand, how would you say that in this case?
How would I say what?
The left hand versus right hand, how would you say that? Like when you do P1 minus P2, do you like if the right hand is.
Oh, okay, well, suppose your first sample is some activity that you've done with your left hand. And your second sample is some activity that you've done with your right hand. And you're testing to see whether or not you can do this activity in, let's say, 10 seconds. Maybe it's assemble a pile of blocks or something like that. So, okay, can I assemble 5 blocks without tipping it over in 10 seconds? So I have a sample of 100 people, and with my left hand, this many can do it. And I have a sample of whatever, and this many can do it. And I'm wondering, can left-handed people do it better than right-handed people? P1 minus P2, what's the true difference between left-hand success and right-hand success? Okay, is P1 minus P2 0? In which case it's the same. Is P1 minus P2 positive, in which case P1 is bigger than P2? Or is P1 minus P2 negative, in which case P1 is less than P2? I don't know. I don't know what P1 and P2 are. But I have a confidence interval, and I can say I'm fairly confident the true value is somewhere in here. Yes?
No, I get it.
Okay, so what is the formula for the confidence interval? Well, it starts off the same way. P hat for one proportion, what was P hat? Was the outcome of my trials. Well, what's the outcome of my trials here? I'm after P1 minus P2, and all I have are these 4 numbers.
P1 hat?
So P2 hat is irrelevant.
No, I think you have both.
So what would it be? What would the outcome be? What would be my estimate that comes from my 2 samples? Just use values here. I don't need words. I don't need long explanations, just things from here. What would the estimate of my 2 samples be? It would be whatever sample proportion I get from the first one minus whatever sample proportion I get from the second one. If you're after P1 minus P2, what's the best possible estimate? P1 hat minus P2 hat. My sample proportion 1 minus my sample proportion 2. What can possibly be a better estimate for P1 minus P2 than the results of my actual samples? Yes? No? Speaking the English? Understand? understand, but have it make sense? Or just, oh yes, those are English words. I understand all of them in isolation, but you put them all together and what the hell are you talking about? Which one is it?
That was like the second example.
Well, I want this. I don't want silence. If it doesn't make sense, say something.
Or, because I mean, P hat.
There's no p hat anymore. P hat was a one proportion
That's
thing,
what I'm saying, it's meant the explanation. With the regular P hat, you would do, X over N.
right?
And then, so then you get the average for one, but now you do two to get the average for.
That's basically it. Yes.
So what is the confidence interval after that?
With what? I haven't finished the formula yet. Right? Plus or minus. I haven't finished my confidence interval yet. You have my sample value plus or minus Z star, same confidence value, plus or minus Z star. And now it gets a little more complicated because now I have this little thing here. This thing here for one proportion involved the sample proportion and involved the size of the sample. Well, it's a little more complicated now because I have two samples. So I have two proportions and two sample sizes.
Then we do, a P hat one person, subtract the P hat two.
Close, but not exactly. Yes.
But you just get the sum of like the P1 minus P2, and then like substitute it.
Not even close, but nevertheless, it's the square root. It's the square root of. Sorry, I can't stop being mean, no matter how hard I try. Okay, P1 hat, 1 minus P1 hat over N1 plus P2 hats, 1 minus P2 hats over N2.
Wait, so how come you can't just like?
Doesn't work out that way. I'm not deriving these formulas. I'm just giving them to you. In the past, I've tried to derive them. And if you think you're confused now, it's nothing compared to the confusion that I've had when I've tried to explain why these formulas work. The beautiful thing about this class is you don't need to know why the formulas work till you actually use them. This is not true in general in math. Quite often when I teach a class, I'm very adamant of proving things because I feel in the most general scenario, understanding why something is true is more likely to make you know when to use it. In statistics, there's no advantage. And therefore, I just give it to you and you go to your calculator, plug things in. You had a question, and I'll do it a question. One
The only
second.
reason you add both this time is because we're trying to find the square root.
On what?
The only reason you add both, you want to have the equation for both,
Well, it's essentially like an extension of this.
so you want to get the square root of both together.
Together, yes. Yes.
What does this formula give you? Like, what do you-
This formula, this is a number. This is a number. So this number minus that number, and this number plus that number gives you an interval. This is a confidence interval. This is no different than what we had here. I am 90% confident that the true value of P1 minus P2 is between this number and this number. That's a confidence interval. Now, if this number contains the number, if this interval that you know what, before we get that, let's do an example. So let me do an example. The sampling distribution for two proportions. So hold on. I'm going to navigate the site here. Okay, here's an example. So I'm going to erase what I have here. Is everyone who's, yes?
Is this, do we have to do it by hand or is it calculation?
Calculator will do all the work, but at least one time you want to do it by hand so that you're convinced that the calculator is doing it correctly. But after that, you just use your calculator and don't worry about it. So here's an example. Interracial dating. It's an example 18.3, which is a continuation of example 18.2. So let me look up 18.2. Would you date a person of a different race? Researchers answered this question for Black males and females by collecting data from the internet dating site Match.com. When people post profiles on the site, they indicate which races they are willing to date. A random sample of 100 Black males. Stop, what do I know? Okay, N1 equals 100. And just to keep it clear what I'm referring to, 100 Black males. And a random sample of 100 Black females. What do I know? N2 Black females. Were selected from the dating sites, with 75 of the Black males indicating their willingness to date white females. Stop, you said, what do I know? X1 equals 75, 75 successes for this experiment. And 56 of the Black females indicating their willingness to date white males. What do I know? X2 is 56. Now on the surface, does there seem to be a difference in proportions between the first group and the second group?
Yes.
56% of Black females are willing to, 75% of Black males. But this is a sample. We know that in a sample, there's always going to be variance that comes from real life. Maybe I got lucky or unlucky in who I asked. So from a statistical standpoint, we have to ask our question, are these two values far enough apart for me to definitively claim, yes, there's a difference? Or are they close enough where I would say, yeah, the sample had a difference, but differences pop up sometimes and it's not significant evidence. So the question says, so is this good evidence that different proportions of Black males and Black females on the internet dating site will be willing to date someone who is white? How large is the difference between proportions of Black males and females and so on? So that was a question in 18.2. And now we are in 18.3, and we are now in the position to answer this question. So let's calculate our confidence interval. Of course, we need a level of confidence, and the question gives a 95% level of confidence. So we are looking for a 95% confidence interval for the difference between these two proportions. We'll do it by hand, and then we'll do it on the calculator, confirming that we do in fact get the same result. So what does P1 have here? 0.75 or 75 over 100. I don't care if you do decimal or fraction. What is P2 hat? 0.56 plus or minus. What is my Z star for 95% confidence? 1.96, right? I think 1.645 was 90%. 1.96 is 95%, and 2.2, was it 2.4? 2 point something.
2.576.
Wait, so is the Z star, Professor,
Yeah,
is the Z star, is it anyway correlated to the Z score?
in a sense. I mean, basically, what we're doing, when we look at 95% confidence, we're saying that we want 95% to be in there. That number there is my Z star. So my Z star is the point that cuts off 97.5% to the left, 2.5% to the right.
And there's a set Z star.
There's a set, well, yeah, I mean, if you don't want to memorize them, you can recalculate them every time. It takes me all of 10 seconds to do it. But if you have it memorized, it's just that much faster. So then we have times the square root of P1 hat, 0.75, 1 minus that, 0.25 over N1, which is 100, plus P2 hat, which was 0.56, times 1 minus that, which is 0.44, also over 100. So let's take out our calculator and let's compute this. So what is my confidence interval? Just let's say 3 significant figures or 3 decimals. From where to where? This calculator work, you shall be doing it. By the way, how long did it take me to do it?
So you're in what you're doing.
I already know what? How to press
The
buttons?
first one.
Am I better at pressing buttons than you? Is that what it is, huh?
The first one will be .218.
I did not get that, but of course I could have made a mistake. But I did not get that. Wait.
For adding it, I got 0.319.
Okay, well, I do get 0.319 for that one.
Subtracting was 0.06.
Yeah, that's what I get, 0.061.
Wait, so is there a certain way when you're multiplying the decimals and dividing them, is there a certain way you can do it, or you just?
I just put in this times this over this, plus this times this over this, hit enter,
Yeah.
square root of that, enter, times the 1.96, enter.
You did square root after.
Yeah, I don't do it all at once, then you have the fractions and parentheses, and it's so complicated. Do it one at a time, one operation at a time. Okay, if you do it all too much at once, then you make one parentheses mistake, your enter is way off, and it's like, okay, where did I, oh, there's an open one there, but we're way too complicated. So what does this tell you? How do I interpret my answer? Yes,
95% sure that the real P1 minus P2 is the value.
I am 95% confident that the true difference in proportions between black males and black females in this regard is somewhere between 6% or 0.061 and 0.319. What number do you notice is not in this confidence interval? What single number is not in there? Okay, you're right, 2 is not in there. Since we're dealing with proportions, if 2 wasn't there, I'd be a little worried. But you're right, 2 is not in there. 17 is also not in there. But there's one number in particular that's not in there that I care that's not in there, which is 0. 0 is not in there. 0 is not in there. And the whole question is, are they equal? Well, if 0 is not in there, how are you going to sit back and say, yeah, they're pretty equal? I think they're equal. They're only equal if you get 0. But all of these numbers are positive, every one of them. The entire confidence interval is on the positive side. So I am 95% confidence, not only that the true value is in there, but even more so that they are not equal. If 0 wasn't my confidence interval, and any value of my confidence interval is as likely to be correct as any other value of my confidence interval, I would say, maybe they're not equal. Maybe they are equal. I can't say they're not. The data does not support that. But here, the data clearly supports the fact that P1 is bigger than P2, and that black males are more likely to date white females than black females. Yes?
Is that a real study?
I mean, it's an example in the book. It doesn't say, it doesn't give a source. But I mean, if I was writing this textbook and I had the ability to actually take real world examples versus making them up, as an author, I would certainly take real world examples. So I will assume that it is valid. Of course, this was also in 2000, doesn't say, but this was years ago when the book was written. So maybe things have changed. You know, these are things that sociologists would study. Now, let's do the same thing with our calculator. When you hit stat tests, which test are we going to use for this one? Which setting under test are we going to use for this one? It's not a t-test. In fact, there's no test here. This is an interval, not even a test. The 2 proportion z interval. The 2 proportion 2 prop z interval. Let's put in our x1, our n1, our x2, our n2, our confidence level. Let's calculate. Well, I mean, they rounded to an extra decimal. But I mean, other than rounding, it's exactly right.
You help with the calculator part.
I mean, just getting what we would just now or what we did before?
I forgot my calculator. A lot of classes last week, so I was behind on.
But I'm asking, are you doing on this calculation or what we just did? Huh?
Whichever one you want to do.
So do you have your TI in front of you?
Yeah.
Okay, stat test. And go down until you see 2 prop z int. It is a 2 proportion z interval. You see that?
How do you get out of the left?
Okay. Stat, test. And you go down to 2 prop z interval. To prop z int, you get it? You see 5 things you have to input, you just input them. So now let's go ahead and address the same question from a hypothesis testing standpoint. All right, let's address the same question from a hypothesis testing standpoint. What would be my null hypothesis here? What would I assume to be true about the currently unknown first proportion value and second proportion value? That they're equal. My null hypothesis is that P1 and P2 are equal. I do not know what they are. I will never know what they are, but my hypothesis is that they are equal. And I am testing right now which of my 3 alternative possibilities. First of all, what are my 3 alternative possibilities? Let's list them. Less than,
equal, or greater.
no, equals not.
I mean, not equal.
Less than, not equal to, or greater. Which one are we testing here? Not equal to. Remember, if you look at the original question, is there a difference? It wasn't are males or females more likely or less likely, is there a difference? So my alternative hypothesis in this case is that P1 is not equal to P2. And I have my same data, the same data. So let's go to the calculator. Which setting on the calculator am I going to use for this one? Huh? Which one? There's 6 tests. The 2 prop z test, the 2 proportion z test. And you'll notice, because we just followed it up from the confidence interval, that all of my data is the same. So all the numbers, my x's, my n's, and my confidence, they're all exactly the same. So I can go all the way down to calculate. And what do I get as my p-value? 0.0047. What does that p-value tell you? Why? No. All p-values are greater than 0. They're all probabilities, right? Probabilities can't be less than 0.
It's less than 5%, so it's significant.
It's less than 5%. It's less than 5%, which makes it a significant result. Why are you shaking your head? I just made a statement. You're questioning me? You questioning me?
I thought it was, no, we couldn't use it if it was less than that.
Huh? Say again, what? You could use what if it's less than what? Be more specific. I don't understand your question.
I thought if it was less than 5% or less than 0.5.
0.05.
0.05, which it is, that it was,
Not significant.
not
Remember,
significant.
if the p-value is low,
you shoot high. That's what Peter told me.
I don't know who Peter is. Whoever he is, he's an idiot, but no. If the p-value is low, the null must go. If the p-value is low, there's no good or bad. There's no good or bad here. We either reject or not reject. You said accept. I don't like that. We either reject or don't reject. And then, of course, reject what? Either reject the null hypothesis or we don't reject the null hypothesis. What do we do here?
Let it go.
We let it go. So we reject the null hypothesis. We conclude they're not equal, which is exactly what we concluded from the confidence interval. Yes.
So in this case, with the p-value, but then that like 0.47%, would that be assuming that they are equal?
We always, when doing hypothesis tests, work under the assumption that the null hypothesis is valid. If the null hypothesis is true, this is how likely our result was. That's very unlikely. You're going to claim the null hypothesis is true when I get that result? Sorry, that's too unlikely. I'm going to reject what you're claiming. Yes.
If it were to be 57, we would.
0.0057 is still less than 0.05. You mean 0.05 with 1 0? If this is higher than 0.05, then we do not reject the null hypothesis. So we say there's not enough evidence to support this alternative.
What if it's equal?
Mathematically, they're never going to be exactly equal. They're never going to be exactly, no. Mathematically, they will never be exactly equal. But to be honest, I've asked that question before, and I don't even remember what the answer was, because I think I was told they're never going to be equal. Don't worry about it. So don't worry about that situation. Yes.
Is it kind of like a gray area? Like if it's between like 0.06 and.
Well, again, 0.05, let's say I have 5% level of significance and it's 0.051. I mean, that's so close to the border that, yes, I have a conclusion of my hypothesis testing, but how much do I want to trust that conclusion? I would probably say, let me do a little more data and have it go one way or the other, and then have a more confident conclusion. Does that make sense? Okay.
It would be too broad.
It would be too,
Too broad,
what does that mean?
because it's close to your.
Well, it's not definitive one way or the other. It's so close to the border. It's like, how do you truly conclude?
I like the 5% testing is like, if it's lower or like, what? Like, yeah.
Speak of the English. What? What are you saying?
Okay, so like, less than 5%, yeah.
Yeah.
Okay, so like that whole like testing is like, if it's greater than a good.
Well, if it's greater, there's no good or bad. We have no good or bad here. We have no personal opinion of what we want the outcome to be. Either the data supports one or it supports the other. If the p-value is less than your level of significance, we reject the null hypothesis in favor of the alternative. If it's not less than, including, I guess, equal, then we do not reject the null hypothesis in favor of the alternative.
So the only way that would be, we would accept it is if.
We never accept it. We either reject or don't reject. There's no accepting
Okay, the only
anything.
way we would not reject is if it was 5%, so like.
5% or higher. Correct.
Yeah, but it's not equal, so like. I'm looking for.
If the p-value is less than 0.05, we reject. If the p-value is not less than 0.05, we don't reject. Not less than will include equals, even though mathematically that will never happen. Ever. So at this point, we've covered one proportion, and now we've covered two proportions. Of course, yes, I saw it drop. Of course, if I want to be complete, I would want to compute how to calculate the z-score for the hypothesis testing scenario, just in case you didn't have a calculator handy and you were stuck on a desert island somewhere and your life depended upon you actually doing a statistical significance test. It can happen. Don't look at me like that. So remember what a z-score is. A z-score is always data minus the mean divided by the standard error. This is every z-score in the history of time. data minus mean divided by standard error. If it's a simple situation, we wouldn't call it standard error, we call it standard deviation. But at the end of the day, even standard deviation is just a standard error. So what is my data? My data is P1 hat minus P2 hat. That is my data. That's the actual value of my experiment. What is the mean if the null hypothesis is true? What is the assumed value of P1 minus P2 if null hypothesis is true? 0. Remember, the null hypothesis says they're equal. So P1 and P2 will be equal. So P1 minus P2 will be 0. And what's the standard error? It's just the thing that we just had there. But you'll notice something now. There's one difference between this and what I had in the confidence interval. What's the one big difference between what I have now? Sorry? Oh, I gotta make one change here. I'm sorry. But one step back. I apologize. This is why we use pencil or we use an iPad so that we can easily correct things because mistakes do happen. We don't know P1 and P2, right? We don't know them. If we don't know them, P1 and P2 can't themselves appear in the formula. You might say, why don't I just use P1 hat and P2 hat? I could use P1 and P2 hat, but isn't it better to use the fact that my null hypothesis is claiming that P1 and P2 are at least equal? So what we do is we compute first P hat. We compute P hat. Now, for one proportion, P hat was simple. Number of successes over number of trials. But now we have P1 hat, we have P2 hat, which is the number of the proportion for the first sample, the proportion for the second sample. So how do I just get P hat now?
You get the P hat of both of them and then divide them.
That is so not correct. But I love the fact that you're willing to put yourself out there and be embarrassed publicly. It really is a braver, huh? But what is X?
It's not include.
There's two samples. What's X?
X1 times X2.
Oh, no, it wouldn't.
We do the sum of both p hats divided by the sum of both.
No, that's so close. I do agree with the denominator. You add the ends. I do agree with that. Oh, wow, that doesn't even make any sense. You add the x's. No. You said x over n. And I said, how could it be x over n? There's two samples. There's no x, there's no n. No, he didn't. He said x1 times x2. I heard it very clearly. You said the sum of proportions. You didn't say sum of x's.
You're twisting my words.
I'm not. I'm using your exact words. See, x over n was wonderful. It's a number of successes over a number of trials. How many successes are there? Well, add up all of the successes. Add up all of the trials. And then we use that. So we have p hat, 1 minus p hat, and then this 1 over n1 plus 1 over n2. This is the formula for the z-score for two proportions, from which I would then calculate a p-value. Of course, our calculator gives us the p-value, so we don't have to waste our time doing it this way. But as I mentioned, I would be remiss if I did not give that formula, even if you never actually use it. Now, remember, when it came time for proportions, we only used the formula for proportions if a certain condition was met. Who remembers what that condition was for one proportion for us to be able to use our general formula? Let's recall here. When could we use the confidence interval formula for one proportion. What was the answer? What was the answer?
Are you related to the NP, right?
I'm asking you. I'm asking you. What was the situation?
More than 10.
What was more than 10?
NP,
NP
and then
or
one
X.
P1, parentheses 1 minus NP.
When the number
Oh,
of
I don't want to twist your
successes-
words this time, so I want to be very clear on what you're saying.
When the number of successes are greater than less, if they're less than 10, you can't use it.
That's it.
Well, there's two different formulas. Yeah, they want it to be greater than 10.
What if they both?
The NP has to be greater than 10, and then I'm forgetting the other formulas.
N times one minus.
Okay, so n times p hat. I don't know p, so they're not appearing in formulas. But n times p hats and n1 minus p hats both must be greater than or equal to 10. If those conditions were not met, if the number of successes and the number of failures were both not greater than or equal to 10, I could not use my regular confidence interval formula for one proportion, but rather I would have to do something else. The +4 proportion. But even the +4 proportion had its own condition. What was the condition for the +4 proportion?
Get that too.
No. That's what we did formulaically.
Wasn't it if it wasn't greater than 10?
Well, yes, I mean, if they're both greater than or equal to 10, we use this one. If they're not both greater than or equal to 10, there still was a condition that had to be met.
Then you use that.
But what was that condition that had to be met? If not, but what was the condition? Look back. What was the condition that had to be met? Yes?
And that'd be greater than 10.
N had to be greater than or equal to 10. Then we used the +4 confidence. So a similar situation arises now. Similarly, to use the confidence interval formula for two proportions, conditions have to be met on the number of successes and the number of failures. What is it? And in the case where those conditions are not met, what do we use instead? Yes.
Wouldn't it do the same thing, but instead of, n plus one and then plus two?
Well, why would I ever do n+1 and n+2?
Or I mean, n1 plus.
Well, so we want to have conditions on n1 p1 hat and 1 minus p1 hat and 2 p2 hats and n2 1 minus p2 hats. In words, what are those four things? In words, how would I describe those four quantities?
Representations of numbers.
Huh?
Representations of numbers.
Well, that's always valid in any, mathematical formula that's going to represent something physically. But in this case, what were these things here? I gave verbal descriptions for these things. What were they?
Successes and.
The number of successes and the number of failures. So what is our verbal description of these four things? Yes, the number of successes and failures for the first sample, the number of successes and failures for the second sample. So they all must be greater than or equal to 10. If not, but, so what would the condition be to use the +4 confidence interval? Close. And 1 and n2 must be greater than or equal to 5. A total of 10, but 5 each. Then we use the +4 confidence interval. Now the question is, what exactly is the +4 confidence interval for two proportions? Not exactly the same thing as the +4 confidence interval for one. I'll give you a second to write this if you have it. Can I erase this up on the left? Anyone still writing it over here? So how do you think I replace P1 hat and P2 hat and N1 and N2 if I'm going to be, and of course, what was P1 hat? Let's write that down. P1 hat was X1 over N1, and P2 hat was X2 over N2. So we have these quantities, P1 hat, P2 hat, and N1 and N2. If we're going to use the +4 confidence interval, how do you think we fix them? Yes. The +4 confidence interval is an adjustment that we make to the original interval that works for small samples. So if this condition is not satisfied, but this one is, then we would use the +4 confidence intervals.
So you like actually.
Yes, but the question is, where do those 4 go? That's what I'm asking. Where do the 4 go? In the case of one proportion, what did we do to one proportion when we added 4? We added 2 where? Top. Well, we added 2 successes
And then 4.
and 2 failures and pretended there were 4 more trials. Right? Remember this? We added 2 successes and 2 failures. We added 4 trials, but we put 2 here and 2 here.
Did you add one to these?
So now
Only one?
we had 1 here. And how many to N1?
1, 2,
2. We add 1 here and 2. And how would N1 change? +5.
2, right?
2. And how would N2 change? +2. So we're still adding 4. But now what we do is we add 1 success and 1 failure to each sample and 2 trials to each sample for a total of 4 extra data points. This would be your +4 confidence interval. And when it comes to the calculator, just plug in your new values for X's and N's as opposed to the original ones, and your calculator will do all the work. Let's do an example of this to see it in action. So this is example 18.6. Abecedarian Early Childhood Education Program. Anyone ever heard of that? Abecedarian? Maybe they made it up. The Abecedarian project was a randomized control study to assess the effects of intensive early childhood education on children who were at high risk based on several socio-demographic indicators. I'm bored already, but yes, people care about this stuff. The project randomly assigned children to a treatment group, which was provided with early educational activities before kindergarten, and the remainder of a control group, to a control group. A recent follow-up study interviewed subjects at age 30 and compared the college graduation rates among earning a 4-year degree. So they took these kids who were babies, and I don't know, they played music by Beethoven, and they had them listen to lectures by Einstein. I don't know, whatever they did. They did like really smart people things. And then they did nothing to these other kids. And then 30 years later, they followed up to find out these graduation rates. Is there a difference? Does it really help imposing all of these smart people things on kids? And we had 2 groups. We had group 1 and we had group 2. This is the treatment group. This is the control group. The treatment group is the one that you did the experiment on. You gave them all the educational stuff. And the control group is the one that you left alone. And we had the following data. There was 52 people in the treatment group and 49 in the control group. Why do you think they weren't the same number, by the way? It could be random. I doubt it's to mess with us. It could be random. It could also be the fact that maybe they started the same and in 30 years, people die. And maybe 3 people in the other group die. I don't know. I'm just spitballing here. I don't know. But for whatever reason, 52, 49. And the number of successes were 12 and 3. 12 in the treatment group and 3 in the control group. And it says give a 90% confidence interval. So 90% confidence level for the true difference in proportions between the treatment group and the control group.
Oh, why aren't you just writing it like in the previous problem format, just like X1?
Because they gave me a table, so I copied the table.
Oh, the, oh,
Okay, I mean, you can do it that way too. It's just no difference. So we want a 90% confidence interval for the true difference in proportions between the treatment group and the control group. So first, am I allowed to use the regular confidence interval here?
no.
Why not?
3
Through what?
plus,
What? I hear what you're saying. What were you saying?
Well, it's 2 different samples, you have to use the 2 samples.
Okay, can I use a regular, good old fashioned two proportion confidence interval here? You say I could.
Yeah.
Did you test the conditions?
Or
What were the conditions that must be satisfied?
that bigger than 10,
What has to be greater than or equal to 10?
and if you have,
Not exactly.
and 1 for, and 1 you have
And what is N1P have representing verbally?
the, that is the successful,
The what?
the successes, and then, and parentheses 1 minus P, and 1 is the failure.
Okay, so how many successes were there in the first sentence? And how many failures were there?
40.
Good. How many successes in the second one?
3.
Can't use it. Right? 3. Not greater than or equal to 10. So next best thing, we drop down to the +4 confidence interval. Can I use that one? Well, what's the condition for that one to be true or to be valid to be used? Huh? What's greater than or equal to 5? Huh? N1 and N2. They're both greater than or equal to 5. We can use it. So let's get our formula for the confidence interval. Normally, I'm going to first write the original one. The regular one, which we can't use, is P1 hat, or you know what? I'll use X's and N's, is X1 over N1 minus X2 over N2. That's P1 hat minus P2 hat, plus or minus Z star, which for 90% is 1.645, times the square root of X1 over N1, that's P1 hat, 1 minus X1 over N1, that's 1 minus P1 hat over N1, plus X2 over N2, 1 minus X2 over N2 over N2. This is the one that I'm not allowed to use. This is the regular confidence interval that I can only use if they're greater than or equal to 10. So instead, I'm going to go to the +4 version. What's the starting point of the +4 version?
Same thing.
Not the same thing.
With the added.
Then tell me what I should write. What should take place instead of X1, which was 12?
You add 1.
So what should it be? 13 over, instead of N1, which is 52.
You add 2.
So it should be 54 minus X2 originally was 3. Now it's going to be what? 4 over N2, which is 49. Now it's going to be what? 51 plus or minus 1.645 square root of X1 over N1 becomes what? 13 over 54 times 1 minus 13 over 54 over
The new N1.
which is 54 plus 4 over 51, 1 minus 4 over 51, all over 51. But we'll do it on the calculator anyway. On the calculator, where do we go on the calculator? Where do we go on the calculator? Where do we go on the calculator? Which one? Stats, test. Now the tricky part. 2 prop z interval. What do I put in for x1? 13. For n1? 54. For x2? 4. For n2? 51. For my confidence level? 0.9. And what do I get? 0.048 to 0.276. What do I conclude? There's no P here. There's no P. I mean, there's a P here, but I don't care about that. What do I conclude?
It's greater than 0.
What is it? Don't say the word it. I hate the word it. Unless you're talking about Pennywise the Clown, in which case that's his name. But in general, don't say it because I know what you're talking about. So what is it? What? Exactly.
That range is.
What range?
Man, what
No, I want you to be clear and specific.
is it called? The interval?
The confidence interval.
Confidence interval is greater than 0.
The confidence interval can't be greater than 0. It's not a number. Only numbers can be greater than 0. The confidence interval is an interval. Intervals can't be greater than numbers.
There's no 0.
Okay, there's no 0 there. So what does it tell us?
I don't know what that's called.
I don't know. You tell me. Yes?
You're 90% sure that the actual P1 minus P2 is within that range.
Okay, now we're talking. It's amazing how eloquence can make things so clear. Yes, question.
Can you explain the plus 4 again? I used to put that up. You did.
I went, these are my formulas here. X1 became X1 plus 1. N1 became N1 plus 2. So instead of X1 being 12, it became 13. Instead of N1 being 52, it became 54, and so on. So what I would conclude if I was writing this, I am 90% confident that the true difference in proportion value between P1 and P2 is somewhere between 4.8% and 27.6%. In particular, since all of these numbers are positive, since all of those numbers are positive, and I feel that the true value is somewhere in this interval, I will conclude that these educational materials work, that the proportion of graduates of the babies who did go through this educational program is greater than the proportion who didn't. You got to eventually take the results of your math and apply it back to the context of the problem. Yes,
So positive means,
just to be clear, you left for the entire problem. You came back at the very end and you're asking me a question on it.
this.
Okay, go ahead.
So positive means the first thing we tested, the first variable was the one that's correct.
Maybe next time you hold it in.
That's-
But no, what it says is, because we're after P1 minus P2, the difference in the Ps, I feel that the difference is positive, which means P1 is greater.
Yeah.
That's it. That's all. Yes. Shortcuts. I love shortcuts.
Like finding the P hat as one of the samples.
Yeah.
If the X is less than 10, would you just project the first condition for like the null P hat? And then use the plus 4?
Oh, yeah, of course. Yeah, I wouldn't go through everything until I see this one. Once I see one that doesn't work, I hone in on it, and that's it. Okay. No, only for cool people. What he said was, why did I go through this and, you know, and before hitting this? Couldn't I just gone right to it? And the answer, of course, is yes. Right? When you're going to your test, you look at the smallest one. Because if the smallest one is big enough, then all the other ones are big enough. But I was just being systematic about it. And to illustrate a point. Yes. Yes,
Why is it called the +4 method?
because you add 4.
You added 2 and then you added 1.
I added 2 to this end and this to this end.
2 plus 2 is 4.
2 plus 2 is
Then
4.
you also added the
No, no,
+1.
these 4 that I added, one went here, one went here, one went here, and one went here. That's where they went. The 4 appear in 2 different spots. Okay? Yes,
So how can we use a p-value for this?
because I didn't do a hypothesis test, I did a confidence interval.
I'm sure you have one.
No, I can do a hypothesis test too. If I did a hypothesis test, I would do it, well, what the hell, let's do it. Let's go ahead and do it. Let's go to our stat tests. Which test am I gonna use? To prop the test. All the data is in there. Go ahead, calculate your p-value. What do you get? 0.024, which is less than 5%. What do we conclude? We reject what? The null hypothesis, and we come to the same conclusion. Okay, so this video that I made, I don't know why the screen is so blurry, but nevertheless it is. That's much. Can I have done that? Okay, I guess as much as the camera. Well, okay, you learn something new every day. Anyways, god damn it. Okay, so I'm closing this down.